So in today's lecture, we'll be talking about a type of series. It's called power series. And this series involves variables, right? So what is this power series and how do we define this power series? So a series of the form summation from n equals 0 up to plus infinity of Cn times x minus a to the power n. And if you expand this, this is just C sub 0 plus C sub 1 x minus a plus C sub 2 x minus a squared plus C sub 3 x minus a cubed plus blah blah blah, where x is a variable, okay? And a, it's a fixed real number. And the Cn's are just constants. We call them coefficients, okay? Is called a power series centered at A, or sometimes power series about A, okay? So again, a power series centered at A, it is of the form sum from n equals 0 to plus infinity of Cn times x minus a to the power n, okay? And if you expand this sum here, you just have C sub 0 plus C sub 1 x minus a plus C sub 2 x minus a squared plus so on and so forth. By convention, we adapt the following. We have x minus a to the power 0. It's always 1 for us, even if our x is equal to a. Okay? So x minus a to the power 0, it's equal to 1, even if x is equal to a. Which means if all the constants here, c sub 0, c sub 1, c sub 2, etc. are present, we have this constant part. Okay? And then, of course, this constant c sub 1 here, it will be the coefficient of x minus a. The c sub 2 here, it's the coefficient of x minus a squared, and so on and so forth. Okay? So an example of a power series is this. You have the sum of x to the n from 0 up to plus infinity. So if you expand this, this is just 1 plus x squared plus x cubed. So this is a power series centered at 0. Okay? Because, well, you can think of this as summation x minus 0 to the n from 0 to plus infinity. So it's a power series centered at 0. Okay? Another example here, we have summation from n equals 0 to plus infinity of x minus 1 to the power n over n factorial. So if we expand this, this is 1 plus x minus 1 plus x minus 1 squared over 2 factorial plus x minus 1 cube over 3 factorial, and so on and so forth. So this is a power series centered at 1 because you see that you have x minus 1 there. Okay? So in here, we are interested on the convergence of power series. Take note that you have variable, you have x here, you have x here. A power series, you have x. So it's a variable, so it can change. Okay? So the natural question is, for which values of x will a power series converge, or will a given power series converge? So you recall from last lecture, we had a particular example, okay, of that type of series. So we are now formalizing that example. So we have a power series there. We had a variable, and then we calculated the values of x for which the power series will converge. So that's the natural question here. Of course, there will be times for some power series, there will be times that when you replace your x with some number, the series will converge. And there will be times that when you replace it with another number, the series will diverge. So we will collect all the values of x for which the series will converge. Okay? So how do we see that? How do we see that? Look at the definition of power series. So you will have the sum Cn x minus a to the power n from 0 to plus infinity. Take note your Cn here, it can be anything. Okay? It can be positive, it can be negative, it can be 0, as long as those Cn's are real numbers. If we expand this, we will have what? C sub 0 plus C sub 1 x minus a plus C sub 2 x minus a squared plus C sub 3 x minus a cubed plus so on and so forth. Okay? And in here, if your x is equal to a, what will happen to the power series? Then, the power series here, C sub n x minus a to the power n from 0 to plus infinity. You look at the expansion here. At x equals a, this will be 0, this will be 0, this will be 0, and everything else here, they will be 0. Okay? And the only one will remain is this c sub 0. So, it's just a constant. Therefore, the series converge. Okay? The series converge. So, this means that um, the series, let us write that series. The series sum Cn x minus a to the n from 0 to plus infinity always converge at x equals a. At x equals a. At the center. Okay? It will always converge at the center. Okay? So the next question is, will there be other places where the series would converge? And do we have assurance, okay, for that? So in order to answer the question, what we're going to do, okay, our process, so listen very carefully. The process is to use ratio test. So use ratio test to determine, okay, to determine the values of x, okay, determine the values of x for which the series will converge, for which the series will converge. Converge. So that's the method that we're going to use. Okay? So there is a question. Will n always have to start at 0 for this series? That is a very good question. If you have a power series, you can start at anywhere. It's just that the most general way of writing the power series is this one. You start with n equals 0. Take note, if c sub 0 equals 0, then you can just start n with 1. If c sub 0, c sub 1 are both 0, then it's good. It's as good as starting with n equals 2. Okay? Etc. But for us, we are defining the power series, the minimum, the lowest value of n as a starting point will be at 0. Okay? The lowest value of n that will have the starting point will be at 0. We cannot have negative starting for n. Okay? Okay? So, now, we said that we will use ratio test in order to determine the convergence of your power series. And there will be 3 possible cases. And only one will be true. Okay? Given a power series, which is, of course, written this way, there are only 3 possibilities. The first possibility is that the series will only converge at x equals a. And for all other places, the series will diverge. That's the first case. The second case, the series may converge everywhere. Okay? The series converges for all real values of x. So whatever x you replace with in the power series here, you will get a sum. So the power series is convergent everywhere. The third case is the following. There is a positive number r such that the series converges only at this interval and diverges at this interval. Okay? So there is a positive number r such that the series converges if the absolute value of x minus a is less than r and diverges if the absolute value of x minus a is greater than r. Okay? So in here, we have this positive number r for the third case. We will define the value of r for the first case and the value of r for the second case. Okay? For the first case, we have r equals 0. If the series only converge at x equals a, we say that r is equal to 0. Now, for the second case, we define r to be infinity. Meaning, if the series converge for all real values of x, okay, then the value of r equals infinity. And of course, for the third case, you will be able to find what the value of r is after doing your ratio test. Okay? We call this r the radius of convergence of the power series. Okay? And the radius will be starting from the center. Starting from the center. Okay? The set of values of x for which the series converges is called the interval of convergence of the power series. Okay? So the set of values of x for which the series converges is the interval of convergence of the power series. Now, let's look at this part here. Let's look at that. Remember, I mentioned last time, if you have absolute value of x less than, say, a, okay, then you have minus a less than x less than a. Of course, in here, your a is a positive number. Okay? Following same argument, from here, this means that we have x minus a will be less than r but greater than negative r. Okay? So less than r but greater than negative r. And if we isolate x here, we will only get x greater than minus r plus a, but less than r plus a. So this means that if you are on the third case, look at this. If you are on the third case here, you found this positive number r, then surely your series, your power series will converge if you choose your x inside this interval. Okay? So if we put this in the real line, for example, this is your real line. Okay? This is your a. R plus a will be somewhere here, minus r plus a will be somewhere here. So the distance from a up to r plus a, that's just r. It's called the radius. And this interval here, okay, okay, will be included in the interval of convergence. Okay? Now, look at this. In the third case, you have absolute value of x minus a less than r. And the other one here, absolute value of x minus a greater than r. What about the one that is equal to r? What about absolute value of x minus a equals r? On that cases, or on that case, or in that case, you are looking at these endpoints. Okay? Why? Well, if you look at this, if you look at that case, absolute value of x minus a equals r, this means that you have absolute, or you have x minus a equals r, or x minus a equals negative r. But this means here, you have x equals r plus a. And then the other guy, it's x equals minus r plus a. So they are the endpoints here. This guy here and this guy here. And what about that? In your ratio test, okay, in your ratio test, this case here is the inconclusive part. Okay? Meaning, using only ratio test, at x equals r plus a and at x equals minus r plus a, the series may or may not converge. So you have to check by substituting the actual value, r plus a and minus r plus a. Okay? Everything good? So again, you are given a power series. There are three possible cases. Okay? And only one of that is true. Either your series converges only at x equals a and at no other points. Okay? Or the series converges for all real values of x. So converges everywhere, whatever your x is. Or the other guy is it only converge on a certain interval, okay? Given by this guy here or given by this guy here. Okay? So let us work on some examples here. Determine the radius of convergence and the interval of convergence of the power series summation n factorial times x minus 1 to the n running from 0 to plus infinity. Okay? So for this, let's just expand this guy here, n factorial x minus 1 to the n from 0 to plus infinity. So at n equals 0, you just have 0 factorial. Plus at n equals 1, you have 1 factorial times x minus 1 to the 1. Plus at n equals 2, you have 2 factorial x minus 1 to the power 2 plus etc. Your 0 factorial, that's just 1, plus your 1 factorial, that's still 1. So you have x minus 1 here. Your 2 factorial, that's 2. So you have here 2 times x minus 1 squared. Let me extend this. Let me add another term here. So for n equals 3, you have 3 factorial times x minus 1 cube plus etc. Now 3 factorial, that's 6. And then you have x minus 1 cube plus dot dot dot. So this is the expansion of this series. Okay? Now, let us determine the radius of convergence and the interval of convergence. So like I mentioned earlier, we will have to use ratio test. So in here, your a sub n, this is n factorial times x minus 1 to the power n. Okay? So we want to find the limit as n approaches plus infinity of a sub n plus 1 over a sub n in absolute values. So this is equal to n plus 1 factorial x minus 1 to the power n plus 1 divided by n factorial x minus 1 to the power n. So my apologies, I forgot to write the limit in here. So let me put that. So limit as n approaches plus infinity. Furthermore, we will do some restrictions in here. We'll have some restriction. Take note that you are putting x minus 1 on the denominator. So in here, we will assume that here, we don't include 1 in the computation. Otherwise, x minus 1 in the denominator will be 0. But anyway, when x equals 1, like what we showed earlier in the more general scenario, at the center, everything here will disappear. And what will be left is this constant there. Okay? So we know at x equals 1, we'll just have to get the constant. But for other values of x, let us solve. Let us solve this. Now notice I did not put the absolute values in here anymore because all of these, oh sorry, I have to put the absolute value also in here because, well, x is a variable, so it can be positive, it can be negative. So we have to put the absolute value. If we simplify this, we will have the limit as n approaches plus infinity, absolute value, n plus 1 factorial, that's just n plus 1 times n factorial. X minus 1 raised to n plus 1, we can write that as x minus 1 to the power n times x minus 1. For the denominator here, we just have n factorial times x minus 1 to the power n. And as you can see, this guy will cancel this. This guy here will cancel this. So we will be left with the limit of n plus 1 times the absolute value of x minus 1. N approaches plus infinity. N plus 1, we can bring it out of the absolute value because n plus 1, it's always positive. On the other hand, the absolute value of x minus 1 is still here. X minus 1 is still within, is still with the absolute value symbols. Because again, your x can be anything. And therefore, x minus 1 can be negative. Now notice, whatever your x is, this is just a constant. Whatever your x is. We are taking the limit as n approaches plus infinity. So this guy here, this is just absolute value of x minus 1 times the limit of n plus 1 as n approaches plus infinity. And this limit here, this is just plus infinity. Okay? So what does this mean? Whatever your x is, except for x equals 1, except for that, whatever your x is, the limit will always be plus infinity. And what can we conclude from ratio test? So by ratio test, okay, by ratio test, the series n factorial times x minus 1 to the power n equals 0 to plus infinity diverges for all x except at 1. So this means that we are in the first case here. The series converge only at the center. So this series converges only at x equals 1. Okay? i.e., so that is the series converge only at x equals 1. So what's this for us? The radius of convergence will just be equal to 0. Okay? So the radius of convergence, By the way, from starting on the next example, the radius of convergence, I'll just write it as ROC. Okay? So the radius of convergence is R equals 0. The interval of convergence, the interval of convergence is actually a single point. Okay? Also, starting on the next example, I will write the interval of convergence as IOC. Interval of convergence. ROC, radius of convergence. Okay? So, the
Sir,
radius is equal to 0 because it's just a single point. It's just
sir,
a single point. Let us consider this next example. Determine the radius of convergence and the interval of convergence of the power series sum x to the n over n factorial n from 0 to plus infinity. If we expand this, we will have, so at n equals 0, you just have 1 over 0 factorial plus n equals 1, you have x over 1 factorial plus n equals 2, you have x squared over 2 factorial plus one more, we have x equals 3, n equals 3, we have x cubed over 3 factorial plus etc. 0 factorial, it's just 1. So this is just 1 plus 1 factorial, it's still 1. So x over 1. So we have x here. Then we have plus x squared over 2 plus x cubed over 6 plus etc. So this is the expansion for that power series. Now we want to find radius of convergence and interval of convergence. So again, your an, this will be x to the n over n factorial. So for x not equal to 0, for x not equal to 0, why x not equal to 0? 0 is the center here. Okay? 0 is the center here. You have x minus 0 to the power n. So 0 is the center. So we remove the center first because from the discussion earlier, the center, it's always a point of convergence of your power series. So what we want to know is what about outside, or what if x is not the center? So for x not equal to 0, we want to find the limit a sub n plus 1 over a sub n. We have the absolute value there. And we let n approach plus infinity. So this is equal to the limit as n approaches infinity of the absolute value. A sub n plus 1, we will have x to the n plus 1 divided by n plus 1 factorial. And then over a sub n, it's the same as times the reciprocal of a sub n. So this will be times n factorial over x to the n. Okay? And if we calculate this, similar to the one we did before, limit as n approaches plus infinity, absolute value, we write x to the n plus 1 as x to the n times x divided by, we write n plus 1 factorial as n plus 1 times n factorial. Then times, we have n factorial divided by x to the n. And then we see here, x to the n will cancel this. N factorial will also cancel this. So we will be left with the limit as n approaches plus infinity of the absolute value of x over n plus 1. And again, absolute value of x, it's just a constant relative to n. Relative to n. Okay? The variable for the limit, it's n. So this absolute value of x, we can bring it out. So we will have absolute value of x times the limit. Let me put this on the next line. We have absolute value of x times the limit as n approaches plus infinity of 1 over n plus 1. And look, as n approaches plus infinity, this is always 0. The limit is always 0. And this is less than 1. Whatever your x is, this limit here will always be less than 1 because the limit here is equal to 0. So, by ratio test, for any x, so this time I'm writing for any x. Because, well, at x equals 0, again, at x equals 0, these guys here disappear. And you'll only get the constant part. So, it's convergent. And if x is not equal to 0, the limit is less than 1. And by ratio test, it's still convergent. So for any x in the set of real numbers, the series x to the n over n factorial and from 0 to plus infinity, this is convergent. So, ROC, radius of convergence, okay? Radius of convergence, your R, it's plus infinity. Interval of convergence, you have from negative infinity to plus infinity. We are on the third case. I mean on the second case of this theorem here. We are on the second case. And on the second case, our R is infinity. Questions? Next.
Sir, I just have a question.
Yeah.
Instead of negative infinity to infinity, can we just have put like all numbers, like the symbol?
Yeah, sure. You can write this. They're the same.
Yeah, that would be acceptable. Okay,
Yeah,
thank you.
of course. You're welcome. So for the next problem, determine the radius of convergence and the interval of convergence of the power series sum x to the n over n from 1 up to plus infinity. So in here, if we expand this, we'll have, take note, our starting point here, it's at n equals 1. Because at n equals 0, this is undefined. I mean, this guy here will be undefined. So we cannot start with 0. So we start with 1. So at n equals 1, you have x over 1. Plus at n equals 2, we have x squared over 2 plus x cubed over 3 plus so on and so forth. The center here, it's equal to 0. Because again, look at this. This is just x to the n. So it's just x minus 0 to the n. That's your center. And at the center, meaning at x equals 0, everything will be 0. So the series, it's just equal to 0. At x equals 0. So now, let's find the radius and the interval of convergence. Ra sub n here, this is x to the n over n. So we want to find the limit as n approaches plus infinity of a sub n plus 1 over a sub n. So we have the limit as n approaches plus infinity of x to the n plus 1 over n plus 1 times n over x to the n. So this guy here, we have the limit as n approaches plus infinity. X to the n plus 1, we'll write it again as x to the n times x. Then, of course, we will have n plus 1 in here. And then times n over x to the n. So in here, we can only cancel x to the n. And for this, we'll just have the limit as n approaches plus infinity, absolute value of x times n over n plus 1. Or this guy here, we have the limit as n approaches plus infinity. Sorry, we'll bring absolute value of x outside. So we have absolute value of x times the limit as n approaches plus infinity of n over n plus 1. This guy here, the limit, it's just equal to 1. So this is absolute value of x. Okay? And by the way, for formality, in here, we have for x not equal to 0. Okay? So that this denominator x to the n here will be valid. Because if x equals 0, we'll have a 0 denominator. But anyway, look at this. For x not equal to 0, the limit of a sub n plus 1 over a sub n in absolute value, it's equal to absolute value of x. Okay? That's the limit, always. Whatever your x is. Except, of course, x equals 0. But we want the convergence of the series. If we want that, it means that we need this absolute value of x to be less than 1. Okay? We need the absolute value of x to be less than 1. Because if it were greater than 1, then it will be divergent because the limit here will be greater than 1 if you chose that. So we will choose that this limit to be something, which is this guy here, to be something less than 1. And that's your possible interval of convergence. In fact, by ratio test, the series will converge. By ratio test, the series will converge for x such that absolute value of x less than 1. Okay? Now, absolute value of x less than 1 implies that your x will be greater than -1 but less than 1. Okay? So we are sure that the series will converge if your x were chosen to be in this interval, -1 to +1. But that's the case less than 1. What about equal to 1? Remember, if the limit of this is equal to 1, inconclusive, you need to choose. You need to use other tests. That translates to testing the endpoints. We are only sure that the series will converge inside. Totally sure, no doubt, because of the ratio test. But what about at the endpoints? Okay? Now, when x equals 1, that's this right endpoint here. Okay? That's the right endpoint. When x equals 1, the series x to the n over n, and from 1 up to plus infinity. So 1 to the n, it's just 1 forever. This is 1 over n. So we have the series 1 over n, and from 1 up to plus infinity. And this guy here, which is this series here, is divergent. When x equals -1, we will have here x to the n over n plus 1 up to plus infinity, n equals 1 up to plus infinity. This is this time your harmonic or your alternating harmonic series. And we've shown that this is convergent. Okay? So what does this mean? We are sure that the series will converge on this. We tested the endpoints. Now we are sure that at x equals 1, the series will diverge. But at x equals -1, the series will converge. Okay? Question? So again, therefore our ROC, it's 1 coming from here. It's coming from here. And then the IOC, it's this interval, including this guy here. And we exclude 1. So IOC will be from -1, including -1, up to 1, but we exclude 1. So this is your interval of convergence. Okay? Questions? Next example here, determine the radius of convergence and the interval of convergence of this power series. Sum x minus 4 to the n over n 3 to the n. So here, your n starts from 1 because you have some n here. So you cannot have n equals 0. So if we expand this, let's just write out the first few terms. N equals 1, you have x minus 4 divided by 3 to the 1. 1 times 3 to the 1. Plus x minus 4 quantity squared over 2 times 3 squared. Plus x minus 4 raised to power 3 divided by 3 times 3 cubed. Plus etc. Okay? And notice, at x equals 4, everything will disappear here. At x equals 4, you just have 0. So anyway, let's solve for the radius and interval of convergence. Here, our a sub n, it's x minus 4 to the power n over n times 3 to the n. So we want to find the limit as n approaches plus infinity. Absolute value, a sub n plus 1 over a sub n. Again here, for x not equal to 4. 4, that's your center. Now we substitute. We have the limit as n approaches plus infinity, a sub n plus 1. That will be x minus 4 raised to n plus 1 divided by n plus 1 times 3 to the n plus 1 times reciprocal of a sub n. That will be n 3 to the n over x minus 4 to the n. Let's rearrange the terms here. Let us combine into a single fraction those that are alike. So in here, we have the limit as n approaches plus infinity. Also, let us write x minus 4 to the n plus 1 as x minus 4 to the n times x minus 4. And then on the denominator, let us put x minus 4 to the n times. We have n. Then on the denominator, you have n plus 1 times. We have 3 to the n. On the denominator, we have 3 to the n plus 1, but let's write it as 3 to the n times 3. And then here, we can see that we can cancel this and this. We can also cancel 3 to the n. So in here, we'll be left with, we have the limit as n approaches plus infinity, absolute value of x minus 4, and then there's a denominator 3. coming from this. And then we have this n over n plus 1 times n over n plus 1. Again, this guy here, it's just constant relative to the variable n. So here, you will have absolute value of x minus 4 over 3 times the limit n over n plus 1 as n approaches plus infinity. Look at this. Again, that limit will be 1. So the limit of the ratio, this is just absolute value of x minus 4 over 3. So this guy here, for x not equal to 4, the limit is x minus 4 in absolute value divided by 3. And we want now to satisfy the conclusion of ratio test. More precisely, we want this limit here to be less than 1. So we want this to be less than 1. So if we can choose our x such that this guy here is less than 1, then the series will converge. But that means you will have absolute value of x minus 4 will be less than 3. Following? So again, you computed for the limit of the ratio. We end up with this limit. Okay? Because of ratio test, we want the series to be convergent. Using ratio test, we want this limit, which is this guy here, to be less than 1. So we have this inequality. And then we just write the absolute value of x minus 4. We isolate that on one side. So the denominator 3 here will go up there. That's why we have this. And this is your R. This is your R. You have absolute value of x minus a less than R. That's precisely the form. So in here, let's just write that. So ROC, that's equal to 3. The radius of convergence is equal to 3. Okay? For the interval, let's manipulate this. Let's solve this. Also, we have absolute value of x minus 4 less than 3. This means that we have negative 3 less than x minus 4 less than positive 3. And then we add 4 to all parts of this inequality. Okay? We have 4 minus 3, that's 1, less than x less than 7. This means we are sure that if we choose our x to be in this interval, the series will converge. Okay? If we choose our x to be on this interval, the series will converge. The next question is, what about at the endpoints? Okay? What about at the endpoints? Now, when x, let's start with 1. When x equals 1, what will happen to the series? When x equals 1, we have the series from 1 up to plus infinity of 1 minus 3, 1 minus 4 to the n over n, 3 to the n. This will be series negative 3 to the n over n, 3 to the n, and from 1 up to plus infinity. Or this guy here, you can rewrite this as negative 1 to the n, 3 to the n, over n, 3 to the n from 1 up to plus infinity. And notice you can now cancel 3 to the n here. So you'll just get the alternating harmonic series. Okay? And again, this is convergent, which is convergent. And then, at x equals 7, when x equals 7, we will have the series 7 minus 4 to the n over n, 3 to the n, and from 1 up to plus infinity, we'll have series 3 to the n over n, 3 to the n, and from 1 up to plus infinity. So this guy will cancel this. We will have the series 1 over n, and from 1 up to plus infinity. Again, this is the harmonic series. This is divergent. So, from here, we are sure that the series will converge on this interval. And then because of this computation, we will now include 1. Because of this computation, we will not include 7. So the interval of convergence will have 1 up to 7, including 1, but not 7. Okay?